record. Okay. So, what I've just handed out, and for those in Dr. Winter's class, he will have these for you as well. Double-sided sheet. One side is headed currents, moving masses of water. That's what we're going to talk about today. And depending on how far we get, we may get into an outline of the second lecture, which has to do with marine habitats. So, today we have currents, moving masses of water. This is an outline of what I'm going to talk about. There's not going to be any place, there's not going to be sufficient room for you to write on this to get down all the information. I just thought I'd provide you with an outline so you can look at it later when you look at your notes and might make putting things together in proper order a little bit easier for you. So, let me get this away. This is for Dr. Winter's group. And this goes over here. And this goes here. And now we can begin. Okay. So, when we think of a current, you kind of think of the water moving in a particular direction. And in fact, that's the case. But we really think of currents on the scale that they exist. For example, let's suppose here's the surface of the water. Here's the surface of the ocean. Here's the bottom of the ocean. You can have a mass of water 1,000 feet deep, or maybe more. Or you can have a mass of water just a couple of feet deep. It's a moving mass of water. It's like a river within the ocean. All right? And this can be moving in this direction, and you can have another current, let's say below it, moving in the other direction. In a way, it's kind of like the wind on Earth. You can have winds, high winds moving in one direction, like the Gulf Stream, and all the other air moving in a different direction. So, currents are moving masses of water, and you can even see, has anybody ever been off the coast near the Gulf Stream? You can go out in a boat, and you can see what looks like a separate body of water right in the middle of the ocean. It has a different color. So, currents are moving masses of water. They can be a mass of water that's shallow. They can be a mass of water that's deep. And currents have extraordinary impact on the life in the ocean, and we're going to discuss those impacts. But what we need to do first is talk about the causes of currents. As indicated on the outline, there are two primary causes of currents. Primary causes of currents. The first cause of currents, come on, right over there. The first cause of currents, you're welcome to use that chair. These little chairs over here are horrendous. The first cause of currents is the wind. Basically, the wind pushes the water. Wind pushes water. And when we talk about the wind, we're talking about the dominant wind. So we'll talk about the prevailing wind. Prevailing wind. What is the cause of wind? Well, let's look at it this way. Let's suppose you're in a convertible on a really nice day and the convertible is parked. You're not going to feel any wind in your face. You know, there's no, if the air isn't moving, you don't feel anything. On the other hand, if the car starts to move, it will seem to you as though the wind is blowing in your face. Even though the air may be still, you're moving against it. Well, this is a good analogy for understanding the source of, one of the sources of winds. Here's the Earth. Here's the equator, just so that we have an orientation. And the Earth rotates from west to east. The Earth rotates from west to east. We are standing on Earth. Here you are, standing right there. And The Earth is rotating from west to east, but the air above it is perfectly still. Just accept that to make it the simplest scenario possible. It's like being in a convertible. If the car is standing still and there's no moving air, then you feel nothing. On the other hand, if there's no moving air and the car starts to move very rapidly, it's as if you have the wind in your face. So here you are, rotating this way, the air above the Earth is standing still, and so your hair is blowing in this direction. To you, the air seems to be moving in this direction. The air seems to be moving from east to west. And it's only because you are moving into that mass of air above the Earth. So, the first cause of wind is the Earth's rotation. Let's simplify this by simply showing the Earth over here, and in effect, the air is moving in that direction. That's as far as we're concerned. The air is moving in that direction because that's the way we perceive it. That's one thing to consider. There's something else to consider, and that is that at the equator, the sun shines most strongly. The equator gets the most heat of any place else on Earth. And so at the equator, what happens is the air warms up and it goes up. The air goes up and then it sinks down in the North Pole and it sinks down at the South Pole. So here is another component of the wind. Basically, the wind is moving this way and the wind is moving this way, from the equator to the poles. Please do not drink in the laboratory.
Sorry about that. I'll put this away.
So it comes down to this. If we were to resolve these two forces, the force that goes from the equator to the poles and the force that goes from east to west, it works like this. Let's suppose you had an object and two strings are attached to it. One string is pulling this way, the other string is pulling that way. Basically, the object is going to move in this direction. We say that the two different forces are resolved in that direction. Well, it works the same way with the wind. We have, in the northern hemisphere, the air moving in that direction and the air moving in this direction, and so the two forces resolve to produce a wind from this direction, a wind coming from the southeast. So we have the southeasterly prevailing wind, the southeasterly prevailing wind. Winds are named from the direction they originate. So this is a southeasterly wind. And then, since we have to consider the southern hemisphere as well, we have the force going this way and the force going that way. This produces a northeasterly wind. A northeasterly wind. These, by the way, are the trade winds. These are the trade winds. When the Europeans first began to explore the Atlantic Ocean and move towards North America, they would hop onto these winds. They would use their sails and catch these winds. So, if you're coming from Europe, you're catching this wind going in this direction. At least it's going in the direction of the Americas. Okay. So, primary causes of primary causes of currents are the prevailing winds. That's one cause, be right with you. That's one cause of currents. The winds are pushing the water. The other thing we need to consider is what is called the Coriolis force. You had a question?
Yes, so I have how many types of winds are there? Just the south, easterly, and north?
Well, here's the way you should think about it. In terms of the wind, you want to think of where the wind comes from. First thing you have to consider is basically the air is standing still, the earth is rotating in this direction. So if you're standing here, basically you perceive wind coming from the east. Second thing you need to consider is that at the equator, the air warms up and goes up and then sinks down at the poles. So that's another major factor causing the wind. Those two factors resolve into a southeasterly wind and a northeasterly wind. Okay? All right. So that's where the winds come from, and the winds are the primary cause, or one of the primary causes of currents. The winds pushing the water. The second thing we need to consider is the Coriolis force. Now, the Coriolis force is the force imparted on the wind and on the currents by the Earth's rotation. It is a force imparted on the winds and the currents by the Earth's rotation. What does that mean? Well, if it wasn't for the Earth's rotating, then we would have primarily this northeasterly and the southeasterly wind, and that would be it. The Coriolis force, however, does something very odd. The rotation of the Earth in the northern hemisphere causes a clockwise flow. In the northern hemisphere, the rotation of the Earth causes a clockwise flow. In the southern hemisphere, the rotation of the Earth causes a counterclockwise flow. Has anybody been south of the equator? Where were you?
I think the Philippines.
The Philippines. Did you notice which way the water went down the drain?
No.
If you're south of the equator, the water goes down the drain counterclockwise. Go home. You never notice this, right? Do you ever notice which way the water goes down the drain? Yeah, goes down the drain. That's all we know, right? So if you go home and turn the water on, let it go down the drain, you'll see that it always goes down counterclockwise. If you go to the southern hemisphere, the water will go down the drain counterclockwise. This is caused by the force of the Earth's rotation. All right, now remember, if the Earth didn't rotate, you wouldn't have this clockwise and you wouldn't have this counterclockwise business. If you're into baseball, you got to take a look at the way the air moves around the baseball. You also have this circular motion. Who's on it? You on a softball team? No?
Soccer.
Soccer? Okay. Doesn't apply to soccer. Anyway, you'll see diagrams of baseballs, which way the air rotates and how you can throw a curveball. All that is impacted by the way you're rotating the ball. All right. So here we have the two primary causes of currents, the prevailing winds and the Coriolis force. Now, in practical terms, what does this mean? Well, remember, we talked early on about the migration of eels, juvenile eels from the Sargasso Sea. All right, so here is United States, there's Florida, there's South America, and over here is where, off to the south of Bermuda and the Sargasso Sea, where those eels are born. And those eels, remember, hop a current. And they move up here, And if they're American eels, they go into fresh water in the Americas. And if they're European eels, they go into fresh water in Europe. Notice they're hopping a current. Current goes up like this and rotates like that. And the reason for it is the Coriolis force in the northern hemisphere. And this current is called the Gulf Stream. It's coming up from around here and moving up all the way around, and that's the current that has a major impact on the distribution of eels. And as you'll see, lots of organisms, lots of marine organisms, depend on currents for distributing them in various places around the world. All right, so this is the Coriolis force imparted by the rotation of the Earth. You could also call the fact that the fact that you have rotation clockwise in the northern hemisphere, counterclockwise in the southern hemisphere, you could call that the Coriolis effect. All right, so the Coriolis force is that imparted by the Earth's rotation. The effect is this clockwise rotation here, counterclockwise rotation in the south. Anybody got a problem with that? No questions? Okay.
Can you repeat what you just said?
Would I do what?
Can you repeat the Coriolis effect?
Sure. Coriolis effect. Well, first of all, let me give. You just came in late?
Yeah.
Okay. Here, come on, take this. Oh, both of you?
I'll get one, yeah.
All right. You need one too? Okay. On the front, typed, is the outline for what we're talking about today. On the back is something we're going to get to. All right, so that doesn't apply, may not apply today, depends on when we get to it. All right, so the Coriolis force is caused by the Earth's rotation, and the effect is that in the northern hemisphere, it causes a clockwise rotation of wind and water, and we're focusing on water here. And in the southern hemisphere, it causes a counterclockwise rotation.
Does the effect also have something to do with the organisms being distributed to where they have to?
Oh, sure, yeah. Just for example, the eel. And the eel starts here and goes this way. And if it's an American eel, the eels go into fresh water in the Americas. If it's a European eel, they go over here. If you didn't have the Coriolis force, then the eels would just be going in this direction. All right? All right. All right, so that's the basics of the causes of currents. Basically, the wind and the Coriolis force. Primary causes of currents, prevailing winds, and the Coriolis force. Now, life would be very simple if that's all we had to worry about. But there are things that also affect the direction of currents. So, what kinds of things affect the direction of currents? Well, number one, obstructions. Affect the direction of currents. Well, pretty obviously, if you had a continent in a way, so here we have North America, South America, and let's suppose the currents are moving in this direction. Well, once they hit the Americas, they got to go someplace else. They don't just hop onto land and go all the way to California. All right? So if you have a continent in the way, that's going to affect the direction of currents. We can even consider here the effect of the topography of continents. And this is something that we've talked about before. Remember, if we go off the coast of Peru, here's Peru, there's the Andes Mountains over there, and you go down the sea like this. Well, the result of air rushing down the mountains and pushing out to sea creates a current that goes out to sea. And that, as you know, winds up creating an upwelling over here. An upwelling would be a vertical current. So you got two things here. In terms of the continents having an effect, if the continents represent an obstruction, then the water's got to go someplace else. They don't go over the continent. And over here, you have the topography of the continents, the land mass, such as mountains over here, causing this mass of water to be moving out to sea. Mass of water is a current. And so here we have a horizontal movement of water, and you have a vertical movement of water, also called an upwelling. So basically it comes down to the fact that the continents divert the currents. And in this case, they divert the wind, which diverts currents. All right, what other obstructions can change the direction of currents? Well, underwater topography. Underwater topography. For example, let's suppose here's the surface of the ocean, here's the bottom, and there's a mountain over here. And let's suppose you have a current moving in this direction. What's going to happen, of course, is this current is going to hit the mountain and then get pushed up like that. So undersea mountains can affect, God bless you, undersea mountains can affect the direction of currents. Also, you need to consider valleys that exist underwater. For example, you know the Hudson River, it's about 6 miles from here. You have to go over it to get into New York. Well, that river pouring out into the ocean has cut a deep valley, an underwater valley, called the Hudson Canyon. And these underwater canyons also change the direction of currents. For example, here we got the surface, here we got the bottom, and here is a canyon, a valley. If a current is moving along this way, when it gets to the valley, it's going to go down. Once it goes down, it's got to come up again, like this over here. It turns out that along the edges of canyons, you have a very high population of benthic organisms. Benthic organisms. Benthic organisms are those organisms that are on the bottom. And the reason you have a high population is the currents are directed by that canyon. And the currents, of course, carries food. And so it allows a high population of organisms to exist on the lip of the canyon. Yes, go ahead.
Can you repeat that part, why they're abundant?
Can I repeat why what?
Why they're abundant?
Basically because at the lip of the canyon, the water is going to be flowing over it. So the water is being directed to come right over here. And in the water, you're going to have lots of particles of food. And so benthic organisms, which are feeding off the material that's in the water, will accumulate here and they will accumulate there. Yeah. Benthic. Benthic simply means organisms living on the bottom. Benthic organisms, we refer to benthic organisms or the benthos, meaning the same thing. All right, so what affects the direction of currents? Obstructions such as continents, underwater topography, and other currents. let's suppose here is the surface, here is the bottom, and we have one current moving in this direction, another current moving in this direction, they're going to collide. So one current has to be diverted. Usually, if this is the heavier current, and we'll talk about what makes currents heavy and what makes currents light a little bit later. If this is the heavier current, this will stay down the bottom, and this will go up and over it. Let's take a look at something else that affects the direction of currents. And that is frictional resistance of the sea floor. Frictional resistance of the sea floor. All right, so you can understand this. Let me ask you something. How many people drive? Okay? Did you ever go along a road and the right side of your car goes over on the grass? Did you ever get over on the grass where the left wheels are over on the pavement, right side on the grass? Never done that. Example noted. Let's then speculate on what might happen. Here are your wheels on the right side. Here are your wheels on the left side. Does anybody have a car that looks just like that? And let's suppose these wheels are on the highway. You got nice hard pavement over here. And these wheels over here are on either the grass or on gravel. And let's suppose you're doing 60 miles an hour. And you're heading down the road like this, and suddenly the right side of the car goes over on a soft surface, or a more friction, a surface that causes greater friction. What's going to happen is this. If you go, well, let's just be simple about it. You have the grass over here, your right wheels are on the grass. Basically, your right wheels are going to go slower than your left wheels. And what's going to happen is the car is going to turn in this direction. Put it another way, this side, the right side, is going to drag behind these wheels over here. And as a result, the car is going to go, you're going to go like this, and you're on the road, you're going to be turning like that. Because these wheels will be going slower than those wheels. What does this have to do with the ocean? Well, if we were to look down on the ocean, here's a piece of the ocean looking down. Let's suppose you had a lot of rocks and gravel over here. And let's suppose over here you had very smooth sand. And along comes a current moving in this direction. What's going to happen is the large rocks and pebbles over here are going to slow the right side of the water down. This is going to move perfectly easily over this, so what's going to happen is the water is going to move like this, and it's going to turn. This turning of the current is a consequence of the frictional resistance of the seabed. Go ahead.
Which way would it turn again?
Well, if we're looking at this illustration, looking down in the ocean, it would turn like this. Here it would turn to the right. Because it's more difficult for this current to move, for this portion of the current to move, than it is for this portion of the current to move. Okay? All right, is that, any clarification needed? All right, let's talk about something else that affects currents. And that is Archimedean forces. Archimedean forces. So, we have to go back to ancient Greek history. Anybody ever hear of Archimedes? Nobody else ever heard of Archimedes? You did, you did, you did? You didn't?
I mean, I might have, I don't know.
Rings a vague bell.
No. Yeah.
I meant to say a vague bell. Go ahead. No, okay. All right, anybody know the story of Archimedes and the golden crown? You wanna tell it or you want me to tell
Or
it?
what's the story again? Archimedes and the Golden One?
Crown.
Maybe.
Well, it turned out that, that the king gave 5 pounds of gold to a goldsmith to make a crown. And the goldsmith made a crown, and it looked great, looked like gold. But the king was suspicious. If the goldsmith had just taken 1 pound of gold out of it and mixed a pound of lead, he wouldn't be able to tell the difference. Because yeah, a little pound of lead, you know, it's 1/20% of the whole thing. It's still pretty much going to look like solid gold. So it's going to be tough to tell if the goldsmith was cheating the king. And you don't mess around with the king. Right? So the king went to Archimedes and he said, Archimedes, I want you to tell me if there is a way for me to know if this is 100% gold or the goldsmith took some of that gold for himself and he just substituted lead for it. Story ring a bell now for anybody? You know it? Yeah? You know the story? Okay. Anyway, what Archimedes did was said, all right, king, I'll think about it. And then Archimedes decided to relax and take a bath. He got in the tub and he noticed that his body displaced a certain amount of water, right? If you ever get in a tub, you won't notice it in a swimming pool because there's too much water. But if you ever get in a tub of water, you'll see that when you get in there, the water rises. You're displacing a certain amount of water. So Archimedes began to think, you know, if I were to take 5 pounds of wood and put it in the tub, it would displace a certain amount of water. And if I were to take 5 pounds of iron and put it in, it would displace a lot less water because the iron is a lot more dense than wood is. So basically, if you have two different materials of different densities, you can tell which material it is by the amount of water that's being displaced. And so what Archimedes did is he took 5 pounds of gold, he put it in a tub, and then he took the 5 pound crown and he put it in a tub, and he found out that less water was displaced by the crown than by the 5 pounds of gold. So he knew that the goldsmith had mixed in another less dense metal in with the gold. And so the goldsmith, I'm sure, did not live too long after that.
Professor?
So Archimedean forces refers to the density, in this case, the density of water. And then when we're talking about density, we're talking about weight per volume. If you got more weight, you know, if you got something that's 10 pounds per unit of volume, 10 pounds per gallon, let's say. Let's do it this way. 10 pounds per gallon, and something is only 5 pounds per gallon, this is more dense. 10 pounds per gallon is more dense. Gallon is a bad, actually I shouldn't have used that, you could get confused. Let's make it 10 pounds per cubic foot per square, per cubic foot. Or 5 pounds per cubic foot. 5 pounds per cubic foot would be less dense than 10 pounds per cubic foot. Okay, had a question? Go ahead.
Oh, nothing. I just was about to say, I do know the story of Archimedes in the tub.
Okay. All right, so water has different densities. That may seem surprising to you. But let's consider what might change the density of water. The density of water depends on two things: its temperature and its salinity. Temperature and salinity. Now, temperature shouldn't surprise you, because you know that cold air is more dense than warm air. Cold air is more dense than warm air. Cold air will be down here, warm air will go up. If we turned on air conditioning in this room, the cold air, and there was no blower, the cold air would be down here and the warm air would be higher. You ever go into an auditorium and it's kind of warm, so if you go all the way up to the top, you know, if it's a slanted auditorium, it's usually hotter up there than it is down here, because warm air goes high, cold air stays low. Well, you can have water in two different temperatures. And in fact, that's the situation that you find in the tropics. Remember, in the tropics, you have the warm water up here. That's the epicline. We talked about this last time. You got the hypocline down here, and right in the middle is the thermocline. This is water and that's water. The difference between these two layers of water is the difference in temperature. And what affects the temperature? Basically, the amount of sun in a particular area. The amount of sun. Sun puts heat into the water. And makes it less dense than water that has less sun, less heat. You could also have air temperatures, which is affected by sun, but I'll make a note of it anyway. Heat will be, water will absorb heat from the air. So you got two things which will increase temperature. The amount of insolation, and that is I-N-S-O-L-A-T-I-O-N, where sol, S-O-L, stands for sun. The amount of insolation and the air temperature both have an effect on water temperature. The other thing that affects water temperature is salinity, how much salt is present in the water.
Does that affect temperature or
What was that?
does salinity affect temperature or density?
Now, we're talking about what affects the density of water. What affects the density of water? Two things affect the density of water: temperature and salinity. So, end of discussion of temperature. Now we'll talk about salinity. What is ocean water? Ocean water is fresh water plus salt. That's what ocean water is. It's fresh water plus salt. You have a question? Go
Can I
ahead.
use the restroom?
Yeah, go ahead. So, let's suppose we had a body of water in a very warm climate, and water evaporates. The water is evaporating, but the salt is staying behind. So basically, this scenario is concentrating the amount of salt. And the more salt you have in the water, the more dense it is. So, the water is becoming more dense because the salt is becoming more concentrated. And by being more dense, it would tend to make this water sink below something where, below another mass of water that doesn't have this situation. Water more dense makes it heavier. It's going to sink below something where this evaporation did not occur. So, here we have salinity increasing as a result of evaporation. That concentrates the salt, makes the water more dense, makes it heavier. So, there is another, almost contradictory, almost seemingly contradictory way to concentrate salt in water. And that is when the temperature is really cold. Here we have the water, here we have the salt in the water. When the temperature is really cold, what's going to happen is icebergs are going to form. And icebergs are pure water. They're not salt water, they're pure water. If you went out to an iceberg, took a chunk of it and melted it, you'd be able to drink it, even though it's formed from ocean water, because it's not the salt water that forms the ice, it is just the water alone. So when icebergs form, the effect is almost like evaporation. Water is taken out and the salt is left behind. So now you have less water, you have the same amount of salt, hence you have greater concentration. Yes?
I'm sorry, can you explain the iceberg?
Yeah, think of it this way.